So homework 12 is due today. No class on Wednesday. I will be out of town again. But the lecture is moved to Thursday online. Thursday evening, 6 to 7 p.m. your time. And I guess homework. I also moved the due date for homework 13. It was supposed to be on Wednesday, but since I won't be here Wednesday, instead of turning it to Pauline, I'll just collect it on Monday. Due Monday, that's December already, right? December 3rd. And then we're going to have our test 4 on Monday the 10th. Because students who need to be exempt from finals need to know early enough. You know, we're having the test like I think probably Friday is already the first day of finals. Did you know that?
When is our final?
I don't know when our final is, but the final exam starts on that Friday. So people are going to start taking final exams on Friday. So, and I don't want to give a test too close to your finals.
Monday, because we don't have your help on Tuesday.
I will.
That's going to be the hardest one. I mean, for the people that got A's, I mean, how they're going to get A's anyway.
See, if I do it on the Wednesday, I'm going to include the last part on the test. I'm really doing this to be it's impact eccentric impact. So
that's going to be on the final anyway.
It's going to be on the final, but at least see, you're going to have 2 homework sets due for that week. Do you understand? Because we have up to homework 15. Okay. If we do the test on the 15th, on the Wednesday, okay, that means that week you're going to have homework 14 and 15, and they're both included on the test. So
There's no win-win situation.
unfortunately, none. Okay. Let's see. Oh, am I forgetting something? Share my desktop. And the hardest part is chapter 16, so you can start studying on that the week before or starting next week, you know.
But I like to have your help.
Yeah, I will be here that week.
Friday?
Yeah, I'll be here. Okay, let's see. So let's look at the last problem that we didn't quite finish last time. Seems like from another eon, okay. So we had this innocent looking problem, right? A single bar in general plane motion. I don't think it can be any simpler than this. Just one bar in general plane motion, okay? We are given its weight, okay, that it moves in the vertical plane and its ends are constrained to follow horizontal and vertical guides. So A is constrained to move along the horizontal and B is constrained to move along the vertical, okay? And there's a 30-pound force that is applied at the position shown where it's initially at rest, and theta equals 30 degrees, and we're asked to calculate the resulting angular acceleration at this position due to the forces applied. Okay, and and as well as the forces on the small end rollers A and B. So we tried, since the problem asks us to find an acceleration, right? Okay, this has to be a chapter 16 problem. We look at the free body diagram and effective force diagram. By the way, the book, if you look at the book, the way they analyze the problems, they right away start with kinematics to either number 1, find all the kinematic variables if you can, or number 2, reduce the number of kinematic variables by relating them relative to each other. I don't like doing that approach because I would like you to see first how much kinematic analysis you need in order to make the free body diagram happy. Does that make sense? So if you right away go to the kinematics of it, okay, Sometimes, if everything is given, you can find all the kinematic variables, kind of like a complete chapter 15 problem, right? If I'm giving the acceleration of A and the angular velocity, and then I'm asking for a force needed to create this type of motion, you know, it's going to be a kinematically determinate problem. I'm calling it kinematically determinate because I can solve for all the omegas, all the alphas, and all the accelerations, okay, by using kinematics alone, chapter 15. So it's what I'm calling a kinematically determinate problem. Okay, and there's probably some unknown external force that the problem is asking you to find. However, in many problems, okay, it's not kinematically determinate, meaning you cannot solve for all the kinematic variables by using chapter 15 alone. And one example of that is this. So instead of trying to do kinematics in order to reduce the number of unknowns, I think it's to your advantage if you can look at the free body diagram and effective force diagram first and determine how many kinematic variables can you afford in your system and still end up with a happy system. Does that make sense? So at least you know before going to the kinematic analysis how much kinematics you need to know before you sum forces, sum moments. Okay? So that's what I recommend, especially for a complicated problem. Okay? So what I've done here is we looked at the free body diagram and effective force diagram at theta equals 30 degrees. Okay? Looking at so I'm going to redo the free body diagram. Okay, so just remember the problem. Yes.
Why are you using AGY and AGX?
Because, can anyone answer that question? Okay. In chapter 15, chapter 16, the Allenberg's principle, okay, FB equals EFD, okay, is very similar to Newton's second law, but on the EFD, okay, you have 2 or 3 things, right? So here it's 2, 1 mass times acceleration of the center of mass, AG, and 1 IG alpha. Okay, it has to always be with respect to G. Is that your question? Okay. Yes, M, it has to be MAG. It has to be the acceleration of the center of mass, not any other point in the system. And it has to be an I relative to G multiplied by alpha.
That's in case of a mass, right?
No, if the center of mass is not moving, then AG is 0. Therefore, it's just an IG alpha. So that's so if it's in centroidal rotation, meaning it's rotating about the center of mass, which means that the center of mass is not moving, which means that AG is 0. Okay, and that's one of the problems that you look at, right? So if it happens that the object is rotating about the center of mass is not moving, A sub G is 0, so you're just going to have IG alpha. Okay? But exactly. So in this example here, if you look at that pulley, okay, the center of mass of the pulley is not moving, right? Because it's rotating about the center of mass. That's why you don't see an AG, mass times AG for the pulley. Is that okay? But if you have a problem that is in this one, is actually a case when the center of mass is moving, right? G can move up. So in addition to the IG alpha, you have the mass times AG. Here, in the problem we're looking at, the center of mass can actually move, right? Yes, it can translate, the G can translate, and we don't know the exact direction of its motion, right? It can move both along the X and the Y direction. That's why instead of showing it as AG with unknown magnitude and unknown direction, I represented AG as 2 unknown components, one along X and one along Y. Is that okay? So I'm going to have to redo the free body diagram because I need a which mass? You can do the cross product if you want. Okay, but we usually do that for the kinematics part, right? In analyzing accelerations in alpha on the right side. On the left side, we don't do cross product. You do cross product in statics when the problem is in 3D. The problem is in 2D.
No, because we have to find alpha and omega, right? That's not
okay, so yes, you can do that, but I'll show you why it's probably not a good idea. It's because Kinematically, the motion of this is not that complicated. There's only one bar, right? I generally use cross products when I have a lot of bars, right? There's only one bar. We'll see what we can do with cross products. Okay. So let's see. So forces acting are NB, NA, 30, and 60. Okay. So I'm just redrawing the free body diagram. So we have a horizontal NB, okay, from the vertical guide, and I assume the NA here to be upward, okay, and there's a 30-pound force that someone is applying, and then the weight of the bar was 60 pounds, okay? And generally, okay, we're going to have a mass times acceleration of the center of mass along X and mass times acceleration of center of mass along Y and an IG alpha, okay? Take note that I am simply assuming the directions of motions here, but I have to sort of be consistent with respect to my assumption. So if you look at the problem again, okay, if you look at the problem here, really, okay, the weight, 60 pounds, the only two things that are given are the weight and the 30 pounds, right? NA and AB are just reactions to those forces, right? So the 30-pound force tends to rotate the bar clockwise, right? Which is going to make what? AGX to the right and AGY upward, right? So do you agree with what I just said? If A is moving to the right, B will be moving upward. If A is accelerating, this is kind of dangerous though, because we're talking about accelerations, right? And you can't really see the relationships between accelerations, right? Because of omegas. In this case, that approach is going to work because omega is actually 0. Right? If omega is 0, the accelerations, relative accelerations are only due to tangential. There's no normal. Remember the case, remember when I showed you for the first time that your visualization of accelerations can actually mislead you, right? And the reason for that is because we actually have 4 terms, right? The acceleration of your pole, right? The acceleration of the object or the point you're looking at, and 2 relative acceleration terms, A sub n and A sub t, right? It's really the relative magnitudes of these terms that determine what the actual alpha is going to be and what the actual acceleration is going to be. But in this case, since omega is 0, right, because it's still initially at rest, okay, so you only actually have 3 terms. Acceleration of the point that you're analyzing, acceleration of your pole, plus the acceleration tangential, right? So you can actually visualize this because there's no normal acceleration. But
if omega was constant, then we would have a tangential goes to 0, but then we would have a normal, right?
Correct. Correct. Okay. If omega is constant, okay, this problem will not make any sense because they're asking us to find angular acceleration.
Then you have a normal.
No, it's angular acceleration. It's alpha. He's like, okay, I'm done. Alpha is 0 because omega is 0. Anyway, so let's just say that I'm assuming this directions of AGX, AGY, and alpha. Okay? And what I want you to do initially is to look at the free body diagram and effective force diagram and decide how much or how many unknown kinematic variables you can afford to have on the right side. So if we look at the Dr. Phil's analysis of this, okay, our unknowns are on the left side, oops, NA and B on the left side, and on the right side we have AGX, AGY, and alpha. It's a rod. I sub G is equal to 1 over 12 NL squared. Okay? So, is this a happy system? No, right? How many unknowns do you have? Okay, how many equations do you have? We have generally 3 equations, right? And what are the equations? Forces along X, forces along Y, and a moment, summation of moments, about a point. Okay? We only have 3 independent equations and 5 unknowns. Okay, this is the time to conclude that in order to make the system happy, okay, if you remember my word of caution before, what makes chapter 16 problem would be this, my triple exclamation point, okay? Before applying the D'Alembert's principle, it may be necessary to reduce the number of unknown kinematic variables, and the unknown kinematic variables will be on the right side of the equation by using kinematic analysis, okay?
So you only use kinematic analysis on the acceleration side, right?
Because only accelerations are kinematic variables. The unknowns on the right side are forces, and forces are not kinematic variables. Okay? So,
It's not constant. What do you do after the summation?
what do you mean what is not constant? Here, nothing is constant. AGX is not a constant, AGY is not a constant, NA is not a constant, NV is not a constant. This entire problem is only for 30 degrees here. At some other angle, all their values will be different. So nothing is constant here. The only thing that's given here is that omega is still 0. But that's going to change eventually because of the angular acceleration that we expect to be non-zero. So of all of these 5 unknowns, okay, that the triple exclamation points that I have, okay, suggest that what? We need to reduce the number of unknowns, okay, by kinematic analysis, okay. The only way we can do this is by reducing the number of unknowns on the right side. So the question now is, how many kinematic variables can I afford to have on the right side and in order to make this system happy?
It's alpha, right?
Well, I'm not solving for anything. I'm simply trying to make this system happy.
Yeah, so you relate NG,
Okay, so, but the question is, how many kinematic variables do we have here as unknowns? Kinematic. 3, right? These 3 are kinematic variables, right? So how many kinematic variables can I afford to be unknown in this system and still have a happy system? Okay. How many unknowns can I afford to have, all in all? How many unknowns can I have? Okay, I can only afford 3 unknowns. Why? Because I only have 3 equations. Is that clear? Okay. 2 of the unknowns are forces. I cannot do anything about those forces without summations. Okay, without applying D'Alembert's principle. So how many additional unknown, which is now going to be a kinematic unknown, can I afford? Only 1, right? Which means that out of all of these 3, I can only afford 1 unknown.
Wait, repeat that. Why can we can only have 1?
We can afford 3 total.
Yes.
This is 1 unknown, and it's a force. It's not a kinematic variable. Here's another one. So I already have 2 unknown forces. How many unknown kinematic variables can I afford? Only 1. Because I should have a total of 3, and 2 of them are forces. Okay? So what I need to do, as you were saying, is we need to express what? Select one of those 3, right? So we're gonna, which one do we select? Alpha, because the problem is asking for alpha, and also it's a lot easier to relate AGX and AGY in terms of alpha, rather than relating AGX in terms of AGY, or vice versa. So we're gonna express AGX and AGY in terms of alpha. Okay? Before I do any summation forces, summation moments, this is the first thing that I need to do. Okay? And if you guys remember, we already did that last time. Okay? So we have to do kinematic analysis. And this is basically a chapter 15 analysis, right? Because we're going to be working with accelerations without references to forces, right? Which means this is just a chapter 15 problem. And what makes this chapter 15 problem slightly more difficult than the chapter 15 problems we did previously is that most of the problems we had before, we were looking for numerical values of those unknowns, right? Here, we're not looking for numerical values of the unknowns because we can't, right? But we need our relationships between this unknown variables. So this is what makes it slightly more difficult than the chapter 15 analysis we did before. Okay? But you still have to master chapter 15 And in doing an acceleration analysis, we still have to go through velocity analysis, right?
But you can
Okay.
do that as cross product.
Yes, we can do that. Yes, you can do that as cross product if you want. If you have time, I will do that. Okay. So chapter 15 for velocity analysis. Luckily for us, what? The omega is 0, right? So not only do we not need to do any velocity analysis, it also simplifies our acceleration analysis because the normal terms will be 0. Okay? So the only two things we know in our acceleration analysis are the directions of A and B. Okay? Acceleration of A can only be horizontal. Acceleration of B can only be vertical. Right? So either one can be used as the pole, right? Because you select as your pole a point of known acceleration, either completely or partly. We have nothing that's completely known. We can only settle for one that's partly known. So we selected A as the pole and analyzed the acceleration of B. Okay, and say that the acceleration of B equals acceleration of A plus 4 alpha, which is what? This acceleration of B relative to A, tangential, is always of magnitude R from A to B multiplied by alpha of the bar. And what else do we know about that? Always perpendicular to the line AB, right? And consistent with your assumed omega, or alpha. Okay? So in our diagram earlier, we were assuming a clockwise alpha, okay, which means that if we're looking at the bar, here's the bar, here's my A, and here's my B, okay, and our alpha is clockwise, okay, what direction of tangential acceleration R alpha would I get? It's going to be perpendicular to the bar, and it's going to be second quadrant, right? That's why if this was 30 degrees, this is also 30 degrees. So the question now that Milene is asking is, can we do cross product? Yes, we can do cross product, but I think it's going to be a lot more complicated. So the cross product would just be what? The acceleration of B relative to A tangential equals omega alpha K cross R from A to B, right? Okay, now just to be consistent with my diagram, I was assuming alpha to be clockwise, so I'm going to put a minus there, right? So the reason why it's going to be more complicated, in my opinion, is that what is R from A to B? It will actually be what? The sine and cosine components of the L, so it's going to be 4 sine alpha, right? 4 sine 30 in the minus in the I direction, because I'm going from A to B, plus 4 minus 4 cosine 30 in the J direction. Do you understand? I actually have two terms, and then I have to do the cross product, where in fact here I can just say it's equal to 4 alpha and perpendicular to the bar. It's right. The only thing is this. The only thing you have to remember is R alpha is perpendicular to the bar, and it's consistent with your assumed alpha. Whether you want to do a cross product or not, in my opinion, it's not worth doing cross product for just one vector, which you know will be along 30 degrees.
But then you end up with only one component in that way?
No, you still have two components. But you know that it's along 30 degrees, so when you do the x and y, you can still break it down. So, but at least, okay, the r is just 4. The breaking down is when I do my x and y components of my vector equation, rather than in finding r itself. Okay?
4 is the length of the bar?
Yes, 4 is the length of the bar, 2 on each side. Okay? So we actually did this and found a relationship between AA in terms of alpha and AB in terms of alpha. That's really not what we want. We needed an AGX, AGY in terms of alpha. Right? But it was necessary to express AA in terms of alpha before we go to G. Right? Because had I not done that, this AA will be an additional unknown which I cannot afford to have. My intention is to ultimately express AGX and AGY in terms of alpha, and before I do that, I better express AA first in terms of alpha, because I don't want to keep that AA as an unknown by itself.
What is AA? The correlation of the bar?
It's acceleration of the end A, point A. Yes. So after expressing A in terms of alpha, I now apply acceleration analysis now going to G, because ultimately it's G that I'm interested in. Okay, so AG is equal to AA plus acceleration of G relative to A. The normal again is 0, and the tangential would just be what? Instead of having 4, it's just 2, right? Because you're going from A to G, and G is now halfway along the length of the bar. And I do AGX and AGY, and we got this results here. Okay, the AGX is positive alpha squared root of 3, and AGY equals alpha. And those are the results that I'm going to substitute in here. Okay, so let's see. This is going to be mass. What is the mass of the bar? It's 60 over 32.2. That's the mass. And AGY is just numerically equal to alpha, right? And this is 60 over 32.2 again for the mass. And AGX was how much? Alpha square root of 3. Okay? So this thing now is being replaced by the blue term, which is now in terms of alpha. This is now replaced by the blue term also in terms of alpha. Now, with AGX and AGY expressed in terms of alpha, this is now a happy system, right? And this is the time when I start my summation equations. And if I remember correctly, Surush suggested, what did you suggest, Surush? Okay? Do you remember? Yes. So some of you would just go summation forces X, summation forces Y, and then summation moments about the center of mass, which is probably what the book would have done also. Okay? But that would require, it's really a happy system now, 3 equations and 3 unknowns. You can set up all those 3 equations and just solve them simultaneously, right? But it's much better if you can solve for one of them independently of the others. So really, if you can eliminate 2 of the 3 unknowns, right, in an equation, use that equation. So he was suggesting we can eliminate NA, okay, and NB simultaneously by summing up moments about the point where they intersect, right? Because there are moments about those points, that point will be 0. So the summation of moments on the left side about point O, that's O, okay, is equal to the summation of effective moments about the same point. Okay, it's very important when you're summing moments, okay, on the left side, it has to be exactly about the same point on the right side. Okay, and does everyone understand why I sum moments about point O even though it's outside the bar? Okay? No? Because NB and A will have no perpendicular distance or moment arm about point O, so their torques or moments about point O will be 0. That will leave us with alpha as the only unknown. Because if I sum moments about point G, right, this is G, all of the summation of moments about point G is equivalent to the summation of moments about effective moments about point G on the right side. Okay, that equation will actually give me what? 3 unknowns. NA, NB, and alpha will all enter that equation. Okay? So it's better to sum moments about point O. If I sum forces along X, I will have 2 unknowns, the NB and the alpha. If I sum forces along Y, I will have 2 unknowns, NA and the alpha. The best equation to use is summation of moments about the point of intersection of the 2 unknown forces, so that those 2 unknown forces will not enter your equation. Okay? And by convention, let's take counterclockwise as positive. Only 2 forces will have moments about point O. NA and AB will have no moments. By design, we selected that point O. Moment of the 60-pound force is positive or negative? Why positive? This is because, yeah, because this force About point O actually creates a counterclockwise. Everyone sees that? Here's the force. About point O, where something moves about point O. That force is going to create a counterclockwise. Okay? Or you can use your right hand. Follow the direction of put your thumb right on top of point O, because that's your axis of observation. Right hand. Right. Okay. Okay. It's going to be pointing towards the positive Z, or counterclockwise. So it's going to be positive 60 times, what's the perpendicular distance? Especially those who haven't taken, what's the perpendicular distance? Here's the perpendicular distance, right? Because a force, the 60-pound force, can actually be moved anywhere along its line of action. So the perpendicular distance will be how much? 2, because this is 2. So the horizontal would become the sine of 30 degrees. Everyone agree with that? When your force is vertical, you expect the perpendicular to be horizontal, right? Perpendicular distance. That's why 2 sine 30 degrees. How about the 30? Is it plus or minus? You can again use your fingers. They will curl this way, and your thumb will be pointing into the, the one. So your thumb will always be on O. See, if my thumb is going this way, I cannot follow the 30 degrees. Yeah, I gotta go this way, so it's into the board, so it's minus. Or you should be familiar with clockwise, like we did in statics, right? So it's clockwise, so it's a minus. What's the force? 30. What's the perpendicular distance? Where's the perpendicular distance of the 30-pound force? About point O. It's going to be this whole distance, right? Yes. The force is horizontal. You expect the distance to be vertical, so it's going to be 4 cosine 30 degrees. Okay? Must be equal to, on the right side, okay, which of the vectors will have moments? Let's not forget this is by itself a moment or a couple or a torque. So I just write that torque by itself without any perpendicular distance because it's already a torque. Okay, and it's minus. Thank you, because it's clockwise. The AGX will have a plus or minus. About point O. We're still about point O. It's minus, right? Okay, minus 60 over 32.2 is the mass multiplied by alpha square root of 3. This is just the effective force itself. Okay, we need to turn that into a torque or a moment by multiplying by the perpendicular distance. What's the perpendicular distance? 2. I think it's cosine. Everyone okay with that? This perpendicular distance here is 2 cosine 30 degrees. And that's how far MAGX is from point O, measured perpendicular to the force. And the AGY will also be minus, right? Okay, minus the effective force, 60 over 32.2 multiplied by alpha. Again, that's just the effective force. We need to turn that into a moment or a torque by multiplying that by a perpendicular distance. Which perpendicular distance would that be? 2 what? Sine 30 degrees. Everyone okay with that? And of course, I didn't substitute it here. We should know what IG is for a slender bar. It's going to be what? 1 over 12 multiplied by its mass, 60 over 32.2 multiplied by the square of its length. Yes? I sub G is equal to 1 over 12 M L squared for a slender run. Okay? And as you can see in this equation, there's only one unknown, so you can solve for alpha. Okay? Once you know alpha, we're not quite done yet because if you remember, it's also asking us to find the forces at the rollers A and B. So we need to find NA and NB. So how would I find NA and NB? Okay, I'm going to do summation of forces along X equals summation of effective forces along X. Okay, so let's do that. What are the forces along X? NB is one of them, plus 30. Okay, must be equal to, those are the only two forces, right? Must be equal to, on the right side, what's the only effective force? It's just the AGX, right? 60 over 32.2 multiplied by alpha square root of 3, right? But this guy here is already known, right? Which means that this summation of forces along X will actually lead us to finding NB. Okay? Similarly, we want to find NA, we sum forces along Y equals the summation of forces effective along Y. Okay, Y forces, we're going to have an NA going upward, 60 going downwards, so it's a minus 60. And on the right side, the only effective force is the MAGY, 60 over 32.2 multiplied by alpha. We already know alpha, which means that we'll be able to solve for it. 60 is vertical. Okay? Any questions about this? So, again, in this problem, my suggestion is very quickly look at the free body diagram and effective force diagram, and then determine how many unknowns can you afford on the right side. Reduce the number of unknowns by doing a kinematic analysis. Okay? And then proceed to summations of forces and moments, and try to make your summations effective by a very effective technique is to sum moments about the intersection of unknown forces. Both of those forces will not enter the equation. Rolling motion. I think there's a similar problem on the homework, but rolling motion is really a special kind of general plane motion. If you are rolling without sliding, okay, what's the relationship between velocity and angular velocity? So if I have an object, okay, and this is, say, the center of mass is G, okay, and if it's rolling about a stationary ground, okay, what that means is, of course, the velocity of the ground is 0, right? So the velocity of the point of tangency is 0, right? If it's not sliding relative to the ground and the ground's not moving, therefore, what the velocity of G would just be R, radius of the disk multiplied by omega. In this case, it's going to be horizontal. All right. Similarly, what can you say about the acceleration of G? We will just differentiate both sides of the equation. Will just be R alpha, and to the right, if I'm assuming that omega is clockwise. Okay. So when it's rolling without sliding, you have an exact relationship between the linear acceleration of the center of mass and the angular acceleration, assuming that it's rolling along a horizontal surface. So let's look at an example. Let's say that I have a, do I have an example here? Okay. Let's say that I have this yo-yo. I actually have the yo-yo with me. Okay. And then I have, let's say I pull it with a force P. Okay, so I have 3 yo-yos here. My hamburger yo-yos. Okay, so it's being pulled to the right, okay, like this. So my question is, where is the yo-yo going? What is the resulting angular acceleration of the yo-yo? Clockwise or counterclockwise? What is the resulting angular acceleration of the yo-yo? Clockwise or counterclockwise? How many of you say it's counterclockwise? Yeah, there's friction because it's fun. How many of you say it's counterclockwise? Raise your hand. How many say it's clockwise? Nobody wants to say anything. Okay. So, by show of hands, counterclockwise is the more popular answer, right? Okay. So, the answer is clockwise. Okay. It's not clockwise.
Well, depending on you.
What? What have you got to say? It's just clockwise or counterclockwise, right? Isn't that clockwise?
What about when he rolls over there?
But it doesn't roll over there. You just say it doesn't. So what happened? Why did you think that it's counterclockwise? Huh? You agreed with Sarush. Okay, let's blame it on Sarush. It's clearly clockwise, right? I'm not tricking you. Do you want to try? So what happened? It's not a trick. Okay? So what you were imagining was something like this. You were imagining as if the yo-yo is pinned at its center, okay, and I'm pulling the, right? Now it's...
You pull the string to the other side.
But I'm not pulling the string to the other side. It's like saying it's yellow. What if it's red? But it's not red, you know. So here's what you're imagining. You're imagining to be rotating about its center of mass, right? If it was pinned here and I pull this, then it's clockwise, right? Okay? Okay, so what happened here? Well, let's inspect the free body diagram and the effective force diagram, okay? So it's going to be equivalent to, okay, so what are the other forces acting on this in addition to the force P? So wait, mg, the normal force. Okay, here's another tricky question. What is the direction of the friction here? To the right or to the left? To the left or to the right? Let's see. If I pull it here, the center of mass moves to the right. Oh, you can't see? I'll give you here. Just don't, make sure you don't eat it. It's my hamburger. Obviously I've had this for years and obviously someone already took one. So is the force of friction to the right or to the left? How many of you say it's to the right? How many of you say it's to the left? No, huh? Beyonce would say to the left, but I don't know if I would trust Beyonce on mechanics. Okay, so those of you who are saying, okay, it's really two opposing tendencies. Remember, the center of mass was going to move to the right. Okay, and those of you who saw that, the center of mass moving to the right, therefore friction must be to the left. What is wrong with that argument? Exactly. Oh, what did you say? Point. So although G is moving to the right, friction is not an issue between G and the surface, right? Friction is actually an issue between the point of contact T here and the ground. So the question now is the point of contact moving to the left or to the right? Well, it's really not moving, right? Because it's in rolling motion. So the tension T, the point of tangency T, where does it want to move? Does it want to move to the left or to the right? What do you think? The point of tangency here. The point on the yo-yo that's tangent to the ground, does that point have a tendency to move to the right or to the left relative to the ground? What do you think? If you focus on the spinning again, it tends to slide to the right relative to the ground, right? Because it spins. It tends to move to the left relative to the ground because it's spinning clockwise, right? If you focus on the fact that G is moving to the right, it's to the left because it's opposite. So which one wins? Do you understand what I'm saying? If you focus on the rotation is clockwise, right? Okay. So with respect to rotation, the point of tangency wants to move to the right relative to the ground, right? Yes? But if I focus on the fact that the whole yo-yo itself is moving to the right, friction is to the left. So there's two opposing tendencies, right? The fact that the center of mass, as the whole yo-yo wants to move to the right, and it wants to spin, right? So which one wins? So is the direction of friction to the right or to the left? Both? Well, it can only be trying to slide to the right relative to, or to the left. What do you think? I'm not going to answer that question. Okay? I'm going to focus on the right side of the equation, which is going to be mass times Ag, right? And an Ig alpha. We already said that the alpha is clockwise, right? And Ag is to the right. Do you agree with my right side? Yes? That I'm confident, right? That the center of mass accelerates to the right and also rotates clockwise, right? So this one I've established, okay? This one here, I still have a question mark. Why? It's not, but what we're concerned is not the motion of the center of mass of the yo-yo. I agree with you, the center of mass moves to the right.
But then the whole thing moves to the right, which is it?
Not necessarily, because as it's moving to the right, it's also spinning clockwise. As it spins clockwise, the bottom part actually slopes to the left relative to the, you agree? Yes? Do you see that? If it's, I take my fingers off. Okay, so it's moving counterclockwise, moving clockwise. If you focus on the spinning clockwise, isn't the friction the other way? You agree it's spinning clockwise, right? What's the direction of friction here? No, left or right? I think. No, it's right. Because this thing here is sliding to the left relative to the right. And the issue is G is not the one that's rubbing against the floor. So whether or not G is moving to the right is really not relevant. Right? So which one is it? To the left or to the right? It spins, okay. Not necessarily. It spins that way because of P, really. The friction is just a reaction. If there was no friction, oh, he's saying that, oh, good point. So if you're summing moments about point G, okay, P is moving clockwise, right? So he's saying that it's to the left. Did you hear what Ben said? And the reason is, if you sum moments about point G, okay, P tends to rotate it counterclockwise, but we know that it's rotating clockwise. Therefore, the friction can only be to the left. You see that? if you some moments about point G, P will make it rotate counterclockwise. Okay. MG will have no moment. N will have no moment. MAG will have no moment on the left side, but alpha is clockwise. Therefore, F can only be the one responsible for spinning it clockwise.
So if alpha is clockwise, then friction's going to be to the left.
Yes.
Then why are you saying move to the right?
I'm trying to confuse you, okay? And I'm trying to make a point that in the case of rolling without sliding, determining the direction of this at this point is not important. Yes. It's initially at rest. Yes. It will make a difference whether it's initially slide. If it's initially moving, it depends on whether is it rolling or sliding to begin with, or rolling and sliding. Do you understand? So let's simplify it by saying that it's not moving. Okay? So my point is, if it's rolling without sliding, I can get away with not knowing the direction of friction initially. Why is that? Okay? If you look at the number of unknowns, what are the unknowns here? On the left side, the normal force is unknown, right? The friction is unknown, right? Because it's rolling without sliding, which means that what? N and F do not have an exact relationship. What I know is if it's not sliding, friction can be less than or equal to mu s n, yes? It's not exactly equal to, yes? It's exactly equal to mu s n if motion is impending, and it's exactly equal to mu k n if relative motion is taking place. If there's no relative motion between the two, it's actually not an equation but an inequality, right? The value of the friction is less than its maximum value, which means that knowing n doesn't amount to knowing f, right? I can know what n is, but I still won't know what f is. So n and f should be counted as separate unknowns, and that's actually a good thing. Because what are the other unknowns? Ag and alpha on the right side. However, there's actually a relationship between Ag and alpha. Ag is just our alpha. Right? So it's actually a happy system with the three unknowns n, f, and alpha, because A sub g is in terms of alpha, which means that I can actually proceed with my equation, okay, and find alpha and n first before finding f. So if I were to solve this problem, I'm going to sum moments about the point of tangency. Equals the summation of effective moments about the point of tangency. What are the forces with moments about point of tangency? Nothing from mg, right, because it passes through point T. Nothing from f, right? Take note, I've left f with no direction at this point. Okay, and nothing from n, because all those three forces pass through point T. The only force with a moment is P, and this is why I answered your question earlier, that P actually makes it rotate clockwise about point T. Yes? Okay, so what would I have now? So it's going to be a minus P times, let's call this distance small r, and call this distance big R, which means that this is actually big R, right? For the R alpha, yes? So what's the perpendicular distance for P if I'm summing moments about point T? It's going to be R minus small r, yes? Must be equal to, on the right side, both moments are clockwise, so I'm going to have an IG alpha minus M times AG, but AG is R alpha multiplied by the perpendicular distance. What's the perpendicular distance? Whoops. It's just big R. Perpendicular distance for this about point P. Okay? Which means that I can find alpha from here.
Why is that the perpendicular distance of big R minus small r?
For P? Yes, because this is the perpendicular distance, which is the difference between the outer radius and the inner radius. Okay, so once I have alpha, okay, I can solve for, even though I can actually sum forces along y equals mass times acceleration along y, which is 0, right? Because the center of mass is moving along the horizontal, which means that the normal force is going to be equal to mg. And then sum forces along x equals mass times acceleration along x, okay? And take note that since f is the only unknown now along the horizontal, I can actually solve for f from a summation equation. And whenever you solve for an unknown equation from a summation equation, for an unknown force from a summation equation, you can actually assume the direction, right? If your assumption is correct, you're going to get a positive value. If your assumption is wrong, you're going to get a negative value, right? So that's why in this particular case, it was not important for me to determine initially what the direction of f is, because I intend to solve for f from a summation equation, and a summation equation will give me not only the magnitude, but the correct direction of the force. Because if I assume the wrong direction, my equations will tell me. I'll just get a negative value for f. Okay? So the rolling motion is actually the simpler case because you do not have to determine the direction of friction. You can assume it. I know your physics teacher tells you never assume direction of friction, right? But in the case of rolling motion, okay, you can actually do it because the force, okay, is not determined from something like this, right? An equation F equals mu Kn or mu Sn does not give you a direction. It just gives you a magnitude. So you have to determine the direction yourself correctly by analyzing the problem. In this case, F is not equal to mu Sn, F is not equal to mu Kn, F is less than some maximum value that we don't know at this point. Which means that knowing N does not amount to knowing F, and F and N are counted as independent unknowns, and F is going to be determined from a summation equation, and from a summation equation you can actually assume its direction because the equation will tell you whether or not the assumption is correct. Clear? Okay, but if it will turn out that F should be to the left, okay, which means that the magnitude of P is actually bigger than the magnitude of M times Ag, only because of the location of where P is. Okay?
Just because of the location of P,
why did I even say that? Because if P were above, because I can have the yo-yo like this, okay, it would still rotate clockwise and would still move to the right. But if you apply Ben's analysis, okay, so for the purpose of people online, okay, Milena's question is, why is it that the location of P determines whether F is going to be to the left or to the right? I'm giving her as an example a case wherein the yo-yo string is up here, okay? And from Ben's analysis, right, if you look at, so here's the friction. I'm still assuming that it's rolling without sliding. Let's put the P to the right also. So it's the same orientation as the other one, okay? So it's like this. Based on my experiment, okay, alpha would still be clockwise and Ag would still be to the right. You agree? So the right side picture would still be very similar. It would still be moving to the right, okay, and would still be accelerating clockwise, yes? Okay? So how do I know now that F should be to the right rather than to the left based on this? Ben can tell you, right? Oh, you don't want him to, she doesn't want you to, okay, I'll tell you why. Okay? Ben, okay, was doing this in his head. I don't know if he was aware that he was doing this or not. But he was actually summing moments, right, about point G. He was summing moments about point G, okay? If I sum moments about the center of the yo-yo, okay, P has a clockwise moment about point G, do you agree?
Yes.
P tends to make it rotate clockwise. Okay. Oh, so it's not clear. So, and I sub G is also clockwise. So how do we know that the friction is to the right or to the left? Well, your analysis doesn't work here. F can actually still be to the left, right? Because I can still have a net clockwise alpha if F, definitely if F is to the left, right? It will help it rotate. But, no, not necessarily. Okay? Because at some moments about point G here, I'm going to get what? P, negative P times R, small r, right? And then plus or minus F multiplied by big R, yes, is equal to Ig alpha minus. I'm saying is if I just look at this equation, it's still possible to make it an equality, right? Whether F is whether F is to the left or to the right. You see? It really depends on how big your P is relative to the Ig alpha. On the other case here, when it's down here, it was clear that F should be to the left. Oh, you're saying that if it's to the left, if it's moving to the right, F has to be to the left? Not necessarily. Okay? It will depend on how. But it might, if it doesn't slip, there can still be a tendency for slip. And the tendency for slip could still be what? So it depends on how. It will depend on, no, it depends on how big P is and how far P is from the center of G. See, the bigger P is, see this, the farther P is away from the center, the bigger the tendency for it to rotate as opposed to translate. Right? Do you agree? The bigger this is, okay, the bigger the tendency for it to rotate relative to. Okay, so it will depend on the relative magnitudes of. But the good thing about this one here is what? If it's rolling without sliding, indeed, I can assume what it is and just follow this step. My equations will tell me whether it's going to be plus or minus. Okay? Because again, my F is going to be determined from a summation equation. Now, what happens when it's rolling with sliding? So if it's rolling with sliding now, okay, and this is my center of mass, and this is the ground, what that means is that the point C, the point of tangency, or we are calling it T, the point of tangency T is not at rest anymore. It's actually sliding relative to. So velocity of T is not necessarily zero anymore because it's moving relative to the ground, okay? Which means that the velocity of G is no longer equal to R omega. And therefore, A sub G is no longer equal to R alpha. Okay? So let's look at the scenario. If we have the same yo-yo, okay, and I'm still pulling it to the right with some force P, okay, and on the right side, okay, so what's going to happen now? If it's rolling with sliding, that means I'm really yanking it, you know, with a big P. It slides, it doesn't roll, okay, if it's a small P. Okay, so what happens now? Forces acting are would still be mg here. There would still be a normal force here, right? There would still be friction here. Okay? Must be equal to, on the right side, I'm still going to have a mass times AG here, and I'm still going to have an IG alpha. Okay, but unfortunately, A sub G is no longer R alpha. Oops, it's no longer R alpha. So on the right side, I cannot do anything to reduce the number of unknown kinematic variables. So if I do a Dr. Phil, okay, what are my unknowns here? On the left side will be N, okay. The F, I will not count as an additional unknown because the F, although I don't know what the direction is at this point, that friction is going to be exactly equal to UKN, right? Because it's sliding. Yes? So there's only one unknown force, N, because knowing N amounts to knowing F, because F is exactly equal to UKN. So we still have three unknowns in three equations. It's still happy system. What is the complication here? We have to establish the direction of friction.
Can we say positive?
You cannot assume anymore. Why? Because, okay, F is not going to be determined from a summation equation. The exact equation you're going to use is that V sub K N equals F. And this equation has no indication, so this does not give any direction. Right? And unlike the previous one, how did we find F? It's from a summation equation. And from a summation equation, even if my assumption is wrong, my equations will tell me that it's wrong because I'm going to get a negative value.
So in that case,
in this case here, what do? We have to know the correct direction of F. And how do we do that? What? Flip the coin. You have a 50% chance of being right or being wrong. Do we do what Ben was doing earlier? Sometimes it works, sometimes it doesn't. Right?
what would be going
He was in his mind showing, I think this is what he was doing.
on?
He was summing moments about point G. Okay? If you look at the summation about point G, there's nothing from N, nothing from MG, positive for P. Right? This one I don't know. When I go to the right side, there's nothing from MAG, but it's negative from IG alpha. Right? The positive moment here cannot equal the net negative moment here unless this friction is providing the negative moment. Do you understand what? So he was doing this in his head, I think. Summation of moments about point T, point G. Okay, he was saying, okay, nothing from MG, nothing from N, and the P, it's going to be P times small r, right? And it's going to be positive. Do you agree? And then for F, we don't know, right? But it's going to be plus or minus FR. It must be equal to, on the right side, there's no moment from MAG. The only moment is actually a minus. Yes? In this case, we're summing moments about point G, right? Okay? And therefore, the only way for this equation to be true, right, is if it's this one. Because a positive plus a positive can never equal a negative. That's why he was saying that the friction must be the one responsible for rotating it clockwise. Therefore, this one is to the left. Yes. Okay? So it worked for this, but it didn't quite work when the P was above, right? Because when the P was above, it's not as clear. Because the P now has a negative moment about point G, right? And that can equal by itself IG that's negative, IG alpha, even though F can be plus or minus. Does that make sense?
Yeah.
So it's not as clear, right? So that's why I said Ben's approach, sometimes it's clear, sometimes it's not. So what are you going to do when it's not clear? We have to know the correct direction of friction. I'm going to tell you how to find it, okay? A little bit. But that thing there, it tells you that it has a backspin, so you know how it's sliding. So this one here, we don't know how it's sliding. You don't know whether it's sliding. We haven't examined it. Oh, good point. I think we have established that it's rolling with sliding at this point. So the third case is you're not given whether it's rolling or rolling without sliding. Okay, so let's go back to this first, okay? How do we establish the correct direction of friction now? Do you understand why we have to determine the correct direction of friction? Because the only way we're going to solve for friction is using this equation, and this equation is true whether or friction is going to the left or to the right. You agree? Okay? And we have to know the correct direction for our solution to be correct. So how do we know the correct direction of friction? No, the summation of moments will not give us any, because the friction has to be determined using this equation. Do you agree? Because I cannot count F as an unknown in my summation equation, Jesus. Okay? Because I already have three unknowns, N, alpha, and AC. How do I find N? Some forces Y. So how do I find alpha? Some moments about the point of tangency. Okay? How do I find AG? Summation of moments about point of tangency. So how do I find the correct direction of friction? The only way I'm going to solve for F is by using this equation. And I have to know the correct direction because I'm going to use it in my summation equation. There's no way to solve for AG, alpha, and N without knowing F. Here, there was a way to have F as the last unknown to solve. And it's solved from a summation equation. Here, in order to solve the problem completely, find alpha, AG, and N, I have to use this equation. And when I use that equation, I have to know whether the F is going to the left or to the right. Do you understand? So let's try and solve this problem. So how would we solve for N? N is easy. Some forces Y equals 0. That will give us N. Okay? How do I solve for alpha? If I solve for alpha, by summing moments about point P, both alpha and AG will enter. And neither one's known. Do you agree? Then I have to use my third equation, which is summation of forces along X. When I use the summation of forces along X, now I don't know what F to use. Is it positive or negative? Right? Do you understand? Because this F summation forces X will have alpha and AG as unknown. The summation of moments will also have alpha and AG as unknown. So I wouldn't know. I will have two possible answers depending on what F I use. If F is to the right, I'll have one answer. If F is to the left, I have another answer. I don't know at this point which one's correct. And have to know the correct direction. I cannot just assume. Does that make sense? Okay, unlike in the previous one, F was determined as an unknown from a summation equation, and a summation equation will give you the correct direction. So any suggestions on how to establish the correct direction of friction here? Yes.
I was trying to solve moments about the point tangent to
If I do that, Jesus, I will have AG and alpha coming in, right? On the right side, AG. No, the axis is actually in the z-axis, not parallel. When you say you're summing moments about point P, you're actually summing moments about under C. Point what? Right here? Well, this will enter, and you don't know what direction it does. It has. Yeah, but it's, in order to solve for either this or this, I have to know this, and I have to know this direction. Because it has a moment about this point. The moment on this side is negative. Oh, he's saying some moments about this point. Okay. We're not sure though, because if it's rolling, you're correct. But if it's rolling and sliding, it's possible that AG would still be to the left. Huh? No, it's not. Even if it's, what do you mean by parallel? It would still have a moment though. You mean, is it intersecting at the point? No, it has a perpendicular distance though. This will enter and this will enter. Yes? Yes.
It's rolling and sliding, and the friction opposes the motion of the object
Mm-hmm.
to the other, what we did before.
Say that again. Oh, yes. Okay, I think he has a point there. If I understand you correctly, this is what you're saying, because he said what we did before. So I think what he's saying is, let's assume first that it's rolling. We know it's not rolling, right? Let's assume that it's rolling. Okay? Solve the problem and find the direction of friction. Okay? Unfortunately, we're wrong because it's not rolling, it's rolling and it's sliding. Right? But he's saying that the direction of friction when it's rolling should be the same as the direction of friction when it finally slides. Does that make sense? Friction is actually preventing sliding. Right? Okay? So during rolling, friction is simply successful in preventing the sliding. But even though when it comes to a point when friction is no longer successful in preventing sliding, the direction of friction should still be the same as its direction when it was successful. Does that make sense? Correct. Okay. So why would it slide here? Because the P that I applied is too big now, right? When the P that I was applying was small, okay, what's going on? Why is it rolling? Because friction was actually doing its job enough. It finally slid because friction was not able to develop enough magnitude, but its direction should still be the same when it was successful. Does that make sense?
So if P is too big, it's still going to
Correct. So friction was still trying to do what it was doing successfully when it was rolling, therefore the direction would still be the same. Does that make sense? So if you cannot establish by looking at it, the problem, the correct direction of friction, what you can do is assume that it's rolling and solve the problem completely. Because rolling will actually establish the direction of friction. Once you get that direction of friction from assumption of pure rolling, that direction should still be the same as the direction of friction when it's finally sliding. Does that make sense? Okay? So it's 12:30. Okay? So was that what you were suggesting? Yes, I did. Yes. So friction is really there in order to prevent sliding. The only difference between rolling only and rolling and sliding is during rolling only, friction was actually successfully doing its job. to what? Apply a force in a certain direction to prevent it from sliding. But even though when it's no longer successful, it should still be doing a similar job, which means that the direction of friction would still be what it was during rolling. Okay? Okay. Let's stop. I think we spent too much time here. Okay.
Professor, have a meeting right now?
I have a meeting, yes, for 30 minutes.
I need 10 minutes with you in private.
Okay.
I'll be in the computer room finishing my homework.
Okay. Don't forget to